So, first time Zoom streaming and recording to YouTube. All right, I feel very important. Okay, so this class, we've got our objectives down. Okay, we should have at this point our diagram down, and now we should be at the end of the basics here. So just to rehash what we have here is we've got this Gerber cell, and I'm showing you one that's been sitting here for a couple days from the bottom side. So I'm going to move that to the side. And we should know that you should never hand in the lab without the objectives. Okay, so make sure that we have the objectives, and there was 3 of them. Okay, number 1 was to make sure that we build and construct a voltaic cell and identify its parts. 2, okay, was to measure the experimental voltage. Everyone built their own Gerber cell or voltaic cell, and you measured that voltage experimentally with a voltmeter or galvanometer. And then 3, we determined the accuracy of results by using percent error. See how close our experimental value was to what was on the net potential table, which we know has limitations, right? It's based on a set of conditions that we definitely were not at. Okay, and this is really important. It's this part right here that we're focused on is the error. Error analysis is big. It's from the errors, party people, that we learn about the chemistry, that we learn from experiments, because all experiments have limitations, but the percent error or the analysis of our errors leads us to a direction where we better understand the chemistry or how the atoms react. It's really important that we embrace the error, okay? All right, now, in this lab, I'm just gonna quickly draw what happened here. I know you have this diagram, and make sure it's correct, because if you're missing some components on the second page, okay, you will lose points on this. So we have this big cell here, okay? We know that we had a magnesium ribbon, piece of solid magnesium. We know that we had this dialysis tubing bag that was tied into a knot. I don't know why it looks like a fish, but I'm not a very good artist. Although I would think bad art is interpreted as good art, right? If we splat some paint on a canvas, it becomes worth a lot. So I'm not sure if I understand it, but hey, that's okay. Now we knew that we put the copper electrode into this bag. We separated the oxidation half cell from the reduction half cell. I don't know if this is brown or red, but in any case, this is my copper electrode. Okay. We put it in a blue solution. I'll make this bag bigger. Okay, of course the blue solution is that I had copper ions. I had copper +2. And because I've used copper sulfate, I also had sulfate ions. And I'll write the sulfate ion without a color, or at least here, SO4 -2. In this beaker, I added sodium sulfate, which we should all know is sodium, and SO4-. We also connected this to a voltmeter. And I showed you this voltmeter had a negative and a positive place to put the leads. And we learned, hey, it's nice to use the red lead, okay, where we think it's positive, the cathode, and then use the black lead where it was negative. If you guys had it switched, you got, in the voltmeters I gave you, no voltage. If I was to give you an electronic voltmeter, you would actually got negative voltage, which would mean you'd have to force it, okay? So we learned that this was the anode, because between magnesium and copper, magnesium had a more, well, where magnesium was on the standard reduction potential, had a lower or a negative reduction potential for Mg+2, which means it had the more positive oxidation potential, or it's lower on the standard reduction potential table than copper. And from our experiences, this was our cathode. We know that electrons always flow from the oxidation half cell. And what's the oxidation? Well, solid Mg0 didn't disappear, but the solid became an aqueous ion in solution. You can't see ions. So it looks, over time, this magnesium became etched, where it was disappearing in terms of the solid becoming the ion. Every time Mg0 became Mg+2, it was pumping, or I should say pushing, doesn't really matter, its electrons this way. Electrons were moving to the cathode. The copper +2 okay, reacted with it. And copper plus 2 is a very strong oxidizing agent. Itself gets reduced and made pure copper. We plated here. Everything we've covered so far. Okay. However, if we don't describe the salt bridge, there'll be 0 voltage here. And of course, there's a salt bridge. There has to be a place that allows ions to flow, and that was the porous what? The porous bag made of cellulose. Cellulose, by the way, is nothing more than glucose bonded to glucose upside down. We call it a beta linkage. But essentially, we got this polymer. We make this fiber going this way and this way. And if we do it enough, we've got these little gaps or places where the ions can flow through. It's a semi-permeable membrane. So, in this oxidation half cell that we identified, okay, we know that the Mg plus is increasing. Well, electrons will never leave something positive, so we need a negative ion to flow. And what flowed, okay, is this sulfate -2 ion left the inner bag and had to move out. That, if this was a solid plastic bag with no pores, you get 0 volts because you needed that negative ion to flow toward the oxidation half cell. And oppositely, or inversely, or just opposite here, in this side, we're losing copper plus 2 ions. Probably for 2 reasons. Number 1, copper plus 2 is what? Diffusing this way. Why would it do that? Well, because it's going from high concentration to low. So some of the copper is leaving us, okay? And is there any proof that the copper left the bag? Yeah, the entire solution is blue, okay? And we'll talk about that problem. But in terms of the copper that we got reduced, the copper plus 2 they got reduced, I should say that specifically, because the copper didn't get oxidized nor reduced. The copper was just like a conductor, just like the platinum was, okay, and the other one I just showed you previous. So the copper plus 2 is disappearing, which means this beaker is getting negative, so we needed the what? Sodium ions that were already in the solution to move through the porous semi-permeable membrane, and that's your salt bridge. If those ions could not get to those respective places, there would be 0 voltage. Well, you measured a voltage experimentally, okay, and you should have gotten something close to 1.7, or, you know, maybe as close as to 2, all right? And those are the issues, okay? So that's that. Okay, so we went back to, I got a cursor here. So now we went, that diagram, make sure you have your experimental voltage put on top of that diagram. And yeah, my computer is lagging. Okay, so now we got a blank page. Oh no, we had a diagram, and now we're going to go onto the conclusion questions. Now, where it says a Grodsky sign-off radio run, don't worry about that. Okay, so make sure you have your experimental voltage, okay, right here. Make sure you have your diagram written with all the things that I asked you to do, and you should be able to see that this is just another example of a voltaic cell. Pretty simple stuff at this point. It wasn't when you first did it. Okay, so let's go to our conclusion questions, okay, which we should have done. Now, I don't know why I did it this way, but you should write your half reaction here, reduction, and then of course, balance your half reaction so that what? The electrons balance by using the distributive property if needed. Get rid of the electrons, and you put the over on there. You should know who got reduced, oxidized, agents are opposite, and then you should have been able to calculate the net potential of that value, okay? I see that some of my students didn't quite get there, all right, but that should be an easy one. You don't need me to know that right there, okay? So clearly, magnesium 0, just to show you, okay, magnesium 0 lost 2 electrons and became Mg plus 2 here. Solid magnesium became aqueous ion here. Copper plus 2 gained 2 electrons. You should be able to do that. Pretty simple, okay? And you should be able to get the theoretical net potential using a standard reduction potential table. I don't have to hold your hand with that, okay? You may say, well, how do I do that? Well, you go to your table, okay? And for those that haven't done it yet, I'll help you out. Okay, and I'll just put this up here. Just stay with me. I just need a standard reduction potential table. And I know some of you have done it. We're all different places, but just make sure we're all together now. Okay, so, and you should have reference tables. I should have them too. Okay, so here comes the standard reduction potential table. And we know magnesium, metal, the anode in this battery, in this example, not all anodes oxidize. And anode just means the what? The place of oxidation. So party people, what we're going to do here is find our copper. And I know it's, for those at home, it's hard to see, but if you look at your standard reduction potential table, copper plus 2 gaining 2 electrons is positive 0.34. Okay? So that's it right there. So positive 0.34. And I keep it as written because that is my what? That's my reduction. The table's written as reduction, so I always keep that. So that's my reduction half cell there. I gotta go find the magnesium. Well, gotta go down a little lower here. Okay, I find my magnesium. I know it's a reactive metal. And I know magnesium's oxidizing, so I'm looking at in this direction. So it's negative 2.37 for magnesium ions reducing, but it's positive 2.37 for it oxidizing. So it's positive 2.37, okay? And you add them together, you get 2.71 volts. And that is what you get for E0 of cell. That just means the net potential of the overall battery, assuming you're at standard conditions. You have 1 molar concentrations. You are at 1 atmosphere. You are at 25 degrees Celsius. If you're not at those conditions, you won't get that. Hint, 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 in terms of what is part of our error. Okay? So I'm taking this off. All right, moving on. Again, you may be hanging out for a second because you may have answered these questions and making sure everyone's on the same page here. Okay? Here we go. So we did a net potential. I need to move this. Okay, now it's moving. So the next question is, calculate the percent error. Okay? For those that don't know, percent error is given to you in the reference table, the Regents reference tables, by the way. Okay? Percent error is nothing more if you haven't done it already. Percent error is our experimental, or what you measured, what you actually measured in experiment, minus the theoretical, or the known, it's the same thing, all over the theoretical, which is the same thing as your known, times 100. So we measured it to be 1.7, 1.8, 1.9. The theoretical is positive 2.71. We divide, so this of course is positive 2.71. I don't know what your value is. And then of course this is 2.71. And of course you're probably off by a volt. Times it by 100, and that is your percent error, which by the way is your third objective. We're seeing how close we are to our known value, which is called accuracy. Accuracy is how close you are to your known. For instance, I don't have it out yet, but rulers are supposed to measure a meter. A ruler that measures a meter is supposed to be a perfect meter. The question is, what kind of accuracy is this? Well, what happens to wood? Doesn't wood warp? It's supposed to measure a meter, but if this is warping over time or chips at the end, this loses its accuracy over time. They actually have in France a meter made of platinum. It's exactly a meter that all meters are based out of. Why do they think they use platinum? It's basically a noble metal. It doesn't react, won't rust, won't chip, okay? And of course it's not going to warp like wood. So how close this is to the actual meter is accuracy. Over time, these lose their accuracy. In fact, a lot of measurement devices lose their accuracy over time. That's why you have to recalibrate them. The electric scales that we'll be using in lab, over time they lose their calibration. I have to recalibrate it, put a known weight on them, and then type in, hey, that's 10 grams. Okay? So all that stuff we talked about. All right. So you should have a percent error. And by the way, you should be a volt off, so about 30-something%. Okay? Percent error. All right? These questions are silly. Who's the anode and who's the cathode, and how you decided which one was which. Okay, I'm not going to help you with that. That's crazy. Now, which electrode do you see disappearing? Well, the one disappearing was the one that was fizzing. Okay, now I've had this one for a couple of days now, but what I will tell you is, when you look from it from the side, I know you can't see, the magnesium kind of fell in because the rest of the magnesium's gone. What I mean by that is, if I can pull it out with some tweezers, all right, and go up close and personal with this, and I'll show you in a second, where did the other magnesium go? Okay, it became an ion. So the actual magnesium that was in here, that was sitting in, okay, is now gone. So if I put it here, get down low, all right. Trying to use every piece of technology I can because it's just fun. All right, and we need to elevate it, like I'm naturally elevated. Probably too elevated now, of course. All right, now, you can't even see it, so I'm going to help you. It's in here. It's fallen to the bottom, but I did not, Christmas. Can I make this more difficult for myself? Where are you? This is like that game. So there's my electrode. And you can see how it's bent. I can hold it this way now. You see how it's bent? Because it was what? Sticking out. Why is it so short? And I'll just kind of put it there so it can stay there. Why is it so short? Can I even see it? I can't even see it. Sorry, I'm talking and assuming you guys can see it. Okay, hold on. And I need to focus, right? Okay. So, here is my magnesium, and it's hard to see, so I'll bring it into the closer foreground here. I'm going to turn it. And there it is in all of its glory. Can we see it now? Yeah. So there is my magnesium sticking out, and it stops right here. Why does it stop? What happened to it? Yeah. When the solution was up to here, some evaporation, the magnesium was very long. And what happened to it over time? It oxidized. So why do you see it disappearing? Because it got what? Oxidized into an aqueous ion. And why? Because magnesium spontaneously loves to oxidize. Why? Think about the first week. Why do things oxidize? Why did this disappear? We know it oxidized. We know the Mg0 went to Mg+2, but why does it? Why is it spontaneous? I want details here. Not about copper. Copper did help it along for sure. Copper was pulling on it and made magnesium oxidize faster, or was more spontaneous doing that on top of it. But the point is, why does magnesium love to oxidize? Force equals K, Q1, Q2 over D squared. What is that? Coulomb's law. Magnesium is a big atom. Electrons are physically, here are the protons, Electrons are physically farther away. Their distance is what? Farther than, let's say, the radius of a nonmetal. So these electrons, think about it, feel the nucleus less by being farther away, or having a big distance, bigger denominator, does what to the force? Decreases the force of attraction between the positive and negative. You make them farther away, they feel each other less. So bigger atoms. So the reason why it disappeared is because it's very good at oxidizing, because it is a big atom where the electrons feel the nucleus less. Or because of Coulomb's law, the distance is increased. That's the details. That's connecting from the first week. We're still talking about Coulomb's law. Okay, number 6. Hopefully I don't go too fast. Stop! Stop! Christmas in July. Christmas in July. Okay. 6. Now this, I have a typo here. In the dialysis, the dialysis will allow, cross out not. Will allow. So, pass through. What physical evidence was there to suggest that it did allow the copper plus 2 ions? Doesn't this entire solution have a hint of blue or green? Absolutely. Okay? This is bluish green, which is basically the evidence that copper plus 2. We know copper ions have a bluish green color. There's a reason for that, and transitional metals have color. But there's a reason for that we'll learn called crystal field splitting or crystal field theory. So clearly the copper plus 2, wherever that bag was escaping. Okay, just like I said. Why? From high concentration to low. Why? Because you're going from a place of concentration, concentrated source to less. Okay. To act as a salt bridge, the membrane must allow sodium atoms to pass through. Why is this essential? Why was sodium needed to get through that salt bridge? To maintain electrical neutrality. To be more specific, though, to replace the positive that was missing when the copper plus 2 became copper 0. It's the same thing, I just want to make sure you understand it. Sodium needed to rush in. It was the only, and honestly, so does what? The magnesium plus 2 jumped in there too. Okay? All good things here. All right. Now, the fizzing. To explain the cause of the fizzing. This is important. Now, I'm not showing you today, but I have a video posted under Thursday where if you look closely, you can see some fizzing in the electrode. So when this electrode was here, there were bubbles. And anytime you've got bubbles, you created a gas. Now, the overall net ion reaction was Mg0, went to Mg plus 2, and then copper plus 2 goes to copper 0. Is there any gases here? We know the solid metals are where the metals are 0. We know that ions are aqueous. There's no gases here. So, if you saw fizzing, which I asked us to do, and if you didn't quite see it, please go to the video, it was fizzing. And the fizzing was due to the fact that a gas was made. Why was a gas made? Yes?
From the water that was dissolved?
Yeah, there was another reaction going on. And we know that water, okay, is very electronegative. Coulomb's law. It pulls in the electrons in the covalent bond. We'll get to these details. Pulls in its electrons. These hydrogens that are in the covalent bond that share electrons kind of have them pulled away. So these guys don't feel those electrons, and that's the positive part of water. This electron-rich area here is the negative part of water. Well, party people, magnesium is good at pushing its electrons. And however, it's important to realize that these positives right here are deficient in electrons. They're seeking electrons. They're good at what? Getting reduced. So there's going to be a transfer of electrons from the magnesium. to the H plus. And so magnesium is going to give an electron to one H plus, okay, and to another of another water. And of course, what happens is, when a hydrogen who's deficient now grabs its own electron, it doesn't need this and becomes H1, or H with one electron. It's called a radical. And we're going to make another one with one electron. And they're going to bond together to make a nice stable H2 gas. So party people, it's important to realize we had a side reaction. Mg was not only pushing its electrons to the car plus 2, it was also using some of its oxidative force to push its electrons onto the H's of water to make hydrogen gas. Okay? That's important. So if the oxidation potential is 2.71, that's its strength as magnesium to push charge electrons around this circuit. If magnesium is using some of its push force, its oxidation or its reducing power force, whatever you want to call it, to push its electrons not to the what? It's using some of its force to push its electrons to the water, then you would say that magnesium's oxidative potential is being compromised. Copper's not being, copper plus 2 is still doing its thing. But magnesium, if it's pushing to the water a little bit, then it doesn't have the same force to do what? Same energy, I should say, to push to the copper plus 2. This value decreased. So it's important to think about in terms of your lab. And you lost a volt in your lab, and partly to do to this side reaction with magnesium, saying, well, heck, why would I push to copper plus 2 when I can do what? Push to the water. So part of its energy to push electrons was used to the water. Remember, we might have ions in here, but the compound in greatest amount is the water. Most predominant species is the water. Okay. Now, let's go to the lab. Talk about the conclusion, because this now covers everything. Now, the conclusion, party people, you can either write by hand or type up, I don't care. But there are 3 parts to a conclusion, okay? 3 parts. Number 1, you're going to tell me what you found in your lab based upon your objectives. We had 3 things we were after. I expect you to make a statement regarding those objectives. Now, I don't need prose. I don't need to say on a warm, sunny afternoon. Get in, get out, say it, and get out. So the first part of this is you tell me number 1. Okay, what did you find? Well, the first was to construct a voltaic cell. You don't need to speak to that. The fact that you have a diagram and you measured the voltage means you did that. I don't need any information there. But the second one was experimental voltage. So I would say the experimental voltage of our voltaic cell was, whatever the number U is, you write that. U is. Whatever voltage you found experimentally. Okay? That covers that. The second part was what? Well, the objective number 3 was to determine the accuracy result, percent error. The percent error for the experimental was 33%, 30%. That's all I need. That's the first part. If you don't tell me in your conclusion what you found based upon your objectives, you didn't what? Accomplish what you set out to do. And I would take a lot of points off. You don't need to be fancy. Just say it. Hey, look at my objectives. Oh, we built it. Okay, the experimental voltage, that's number 2, was. The percent error is. Boom, done. Second part, okay? The second part now is the error analysis, okay? And this is where I'm going to pick it apart. You do not list the errors. I do not want you to just list and tell me the errors. I want you to list the error, and based on your knowledge of what you understood and learned in the last 2 weeks, explain to me how that error contributed to your result. The first thing I would do is say, hey, and by the way, that percent error should not be positive. Because our measured voltage was under the experimental, because our experimental voltage that we measured was under what we got from the net potential table, I expect you to report a negative value. And so the first thing I would say is the negative % error demonstrates that our voltaic cell did what? Produced a voltage far less than what was expected due to many possible errors. I'm looking at that negative. If it was positive, I would say, hey, we were way above what was expected. And now I expect you to talk about in your lab what now has led you, in this case, to be under the voltage. What do you think? Don't just list. Don't just list. Okay? So I would say, number one, okay, the big elephant in the room is the fact that there was a second reaction. And I kind of covered that. Okay, so that's number one. It's an easy one. Okay? What limited and made my voltage far less than what was expected? Well, one contributing is that second reaction, which we know occurred because there's a gas and there's no gas here, contributed to it. That's not enough, though. Explain how. Explain why the voltage was less. I kind of did that. Okay? And it's the video again, so play it back. Okay. What other errors? I'm going to give you some hints. Well, this is blue, isn't it? So, copper plus 2 was diffusing out of the bag, wasn't it? Okay? So, if copper plus 2 concentration, the Chatelain's principle, here's the stress response. If copper plus 2 concentration was going down by it moving by diffusion out of the bag, what is the response? To make more of it, which now makes this shift where? If I need to make more copper plus 2 to regain my, yes, what is that going to do to my expected voltage? That's right. Okay, something else, party people, to talk about. Okay? Now, as we lose copper plus 2, either by diffusion or by the copper plus 2 becoming a copper solid in reduction, okay, we know this bag is going to get negative. Well, we need something to come in there to counterbalance. Well, we know that there's sodium comes in there. Well, so does who? Magnesium's coming in there too. Now let's think about this for a second. If magnesium goes into the bag as plus 2 ion, what ion is in there? Okay, I'm sorry. Copper plus 2 and what else? Sulfate. Okay? What do we know about copper sulfate? Okay? Is that soluble or not? Why don't you look that up? Okay? I'm going to leave that alone for you. Okay? It may or may not make it precipitate. All right? Also, there's some other contributing problems in here. You see some precipitates in here. Some things settled to the bottom. Okay? Looks like there's some blue precipitates. So there seems to be some blue precipitates. The copper theoretically is bigger, but you got some blue precipitates here. Okay? Now, I'm going to help you with this one. Okay? When magnesium, one magnesium here, gives off an electron, it gives it up to one water. Water loses an H, and it makes remaining a hydroxide. Hydroxides plus any metal make, that's not a group 1, makes a precipitate. Let's look over here for a second. I don't know if I can do this. But if you go to table F, you'll find hydroxides to the left. All right? Hydroxides. Now think with me for a second. In the reaction, here's the reaction, and we're almost done here. The reaction is occurring. I'm going to get rid of this right here. Okay? Here's the reaction with water. So you know, magnesium plus water is going to make MgOH2 2 waters are involved. Okay? And it's going to make hydrogen gas. That's the reaction. Okay? Now the question is, what's this? Well, really it's Mg plus 2 and hydroxides. Now we know hydroxides will make it precipitate. Table F, look it up. That may help your overall reaction a little bit. But some of these hydroxides that don't hook up with the magnesium could do what? Can go into the bag. And when they go into the bag, they react with copper. Okay, so a lot of this copper stuff in the bottom is copper hydroxide, which if you go to table F, okay, is insoluble. Hydroxides are really small ions. They're -1, but because they're so small, they coulombically attract. All right? Something else, and then one more thing, I'm done. In order for this to equal, let's pretend no issues that we just talked about here. Reacting with the water, making it precipitate, the copper leaving. How about another issue? Let's say that all that didn't occur.
Standard.
Are we at standard conditions? Were we at 25 degrees Celsius? No. And were these 1 molar? I know I didn't make. Now, how did you know they weren't 1 molar? Were we under what we're supposed to have? So you can probably guess that I didn't have 1 molar solutions. Okay? So I'm giving you a lot to think about, but take those errors and cohesively explain in this example why it was less. Don't explain to me why it was more. Don't give me an error and explain, hey, that makes it go forward. Okay, now I know that one of these I talked about could possibly have done that. And also magnesium sulfate, although it may be soluble, it's not very soluble. Some of it does precipitate out. Okay, so I'm asking you now to make an error analysis. Okay, and so what you're doing is very simply is not listing the errors, explain them. All right, and I've given you plenty of hints here. All right, and that's it for the lab. If you want to type it out, fine. If you want to write it, you can. You may need more space, and I will rip apart your conclusion if you do not write correct chemistry, if you don't explain in detail. What I mean by that is explain it. Don't just list it. Hey, the error is that the copper left the bag, and that, lowered the concentration and the voltage drop. How did the voltage drop? The voltage dropped because of Le Chatelier's principle, dropping the copper plus 2 made the reaction shift to make more. You need to talk and fit the steps in. Hey, see you later. Great job. This is due Monday. Okay? Did I ever put this on? Leave meeting. All right, whatever. Looks like I got the video though, hopefully.